All right, then let's begin. Hello everyone. Hope you're doing well. Hope you're staying safe. Let's get started. You guys have a big day ahead of you, right? You have a test this evening. So I kind of want to jump in right now because towards the end of today's class, I'm going to talk about something that might help you with a bonus problem on that test. So let's make sure that we actually get to that point, and hopefully we have 5 or 10 minutes at the end where you can ask me about any logistical concerns regarding the test. But hopefully you guys by today got all the online stuff to work out. And yeah, so let's share the screen. And as usual, I'm going to turn off my camera to make sure to reduce the glitchiness here. Patrick is coming in, so you can listen to my soothing voice talk about mathematics. So we're going to talk about the dot product today, which is very interesting, very excited about it. Hopefully you guys understood that lecture on vectors. We just went through the basics, and we're going to be using some of that today. And we're going to talk about the dot product. But before we get into the dot product, and tomorrow I also want to cover the cross product, I do want to kind of motivate a little bit where these guys come from. So even when I was a student, and I see it all the time, normally someone introduced one of these guys, the dot product or the cross product, they kind of just tell you the definition, and then they just go into using it, and you never have any appreciation for where it comes from or why it's important or why it even does what it does. So I thought it would be fun to actually talk about some motivation with you guys before we begin. One thing you guys would have seen since we've been dealing with 3 dimensions, and since we've been talking about 3 space, is that things are similar but different. There are some ways in which things are similar. So for example, the rectangular coordinates in 3 dimensions is very similar to the rectangular coordinates in 2 dimensions, although yes, there's a 3rd component to worry about, but conceptually that's very similar. But we've seen things that are kind of different. So for example, the equation x equals 1, we know that in 2D to be a line. It's a vertical line passing through x equals 1. However, once we go to 3D, we really see the truth. That is actually a plane that is parallel to the YZ plane. And if you look at an equation like x squared plus y squared equals 4, in 2D, we know that to be a circle. Turns out in 3D, that's actually a cylinder, and so on and so forth. And so there are many things where it's kind of, yeah, it's kind of the same, but kind of different. And there is clearly some sort of translation that we need to go through when going from 2 dimensions to 3 dimensions. And vectors, to kind of tie in what yesterday's lecture was about, vectors is indispensable in describing locations and things like that in 3 dimensions, because they kind of they kind of address that issue. So for example, once you know how to write the equation of a line in a vector form, which you would learn in the next class, then no matter what dimension you're living in, that equation is going to look the same. It's going to be interpreted as the same thing. As opposed to you're in the situation where, oh, x equals 1 in this dimension is a line, but in that dimension is a plane. And you won't have this, this weird kind of notational difficulties to go through. So vectors are very, very important in that regard. And we don't normally want to describe things in terms of equations necessarily. It's very often convenient to describe things in terms of vectors. So instead of looking at describing all points that are a distance of 2 units away from the origin by the equation x squared plus y squared equals 4, instead we can just describe them. Here's all points that are at the tip of this position vector. And we want to describe that position vector in such a way that whether we're looking at it in 2 dimensions or 3 dimensions or 4 dimensions or n dimensions, things are actually very similar. So vectors are very important. Another thing that you'll notice is that our functions, we will have objects like this to worry about when we're in 3 dimensions. And we're used to functions looking like y equals f of x and so on and so forth. But in our higher dimensions, you'll realize that sometimes you'll have surfaces and functions that look like this guy. where we have two inputs, right? So, and there's a third output. So you can imagine that there is some coordinate in the xy plane, x comma y, and then when you plug that into the z function, it outputs some z coordinate, and that tells you that point is on the surface. And now our domain in such a function might be a region in 2 space, right? So when we're normally used to thinking of our input space as just some interval on the real line, some interval on the x-axis, okay, my domain is this set of x values that are on the x-axis. Now we're in a situation where our input space is 2-dimensional. And so now we have to go through this whole translation about what does it even mean to be a domain anymore, and how do we actually treat a domain and all that good stuff. We need to know about all those things, okay? So vectors are important, but now we want to do calculus, okay? And we want to do mathematics in 3 space, and we want to know how all these things are going to work, how are they going to fit together. And so now let's stick to a calculus context because we're in calculus class. We want to be able to do all the things that we could have done in calculus before, back in 2 dimensions. So what were the things that we wanted to do in calculus? The main things were derivatives and integrals, right? And so now we have to figure out, okay, what would it mean? What would we need to be able to do to talk about derivatives and integrals and similar things in higher dimensions? Well, what was a derivative? It was a way to measure slope. What is a slope? Well, it's kind of a way to measure the direction that a curve is moving. Is it increasing? Is it decreasing? And from that, we can talk about all sorts of qualities and properties of a curve. And what else do we like to do? Integration. And what was integration? It was a way to find an area under a curve. How did we actually put this together? Well, going back to Calc 1 a long, long time ago, remember we used to set up Riemann sums to get an integral. What did we need to do? We need to take an interval on the real line, on the x-axis. There is some interval that we want to find the area under a curve, say a to b. We sliced up that interval into quote unquote subintervals. Then we measure the area of rectangles that we put on those subintervals. So you'll realize there are some things that we need to be able to do. For example, we need to be able to talk about directions on a surface or a curve in 3 space. And we need a good way to do that. We also need to be able to, pretty much just like how we did back in Calc 1, be able to dissect an input space in such a way that we can create an integral on it. Now, of course, if you're on the real line, creating subintervals, that's a whole other story. But in 2 space, a nice way to dissect things is to just dissect them in 2 directions. And instead of having subintervals, now what you'll realize when we start dissecting this input space, we have these little patches, and we can talk about how those patches relate to our function. And so there's an input space that gives you this patch over here. And then there's another part of the input space that gives you this patch over here. And so now we're in the situation where we want to be able to dissect our input space so that we can talk about doing things like creating an integral. And so now you realize, okay, so if I were to dissect my input space, what would I need to be able to do with that input space? Well, you might have remembered when we're finding Riemann sums, we need to find something called delta x, which means we had to have a way to measure the dissections in our input space. So we have this interval AB, we slice it up into subintervals. We needed a way to measure those subintervals. And for us, the important measuring characteristic was length. Now here, if we have patches, we have these little patches, an important characteristic now becomes area. So to be able to talk about these things in 3 space, there are a couple of things we have to be able to do. We have to talk about directions in which things are moving. So there is a patch. There's a patch somewhere over. Oh, you dropped the pencil. Okay, so there's a patch somewhere over here, right? How can I describe what direction it's slanted in, right? And moreover, if I were to talk about the part in our input space, how can I measure the area of that patch, right? So these are the things that we want to be able to do. We want to be able to talk about the areas of our dissections. We want to be able to measure them. We want to be able to tell what direction they're slanted in. What does it even mean to slant in a direction anymore? Is there a notion of slope? in the same way as we had it in 2 dimensions? All those kinds of questions that we're going to answer. Now, the question of slope, you are actually going to answer that more in the next class. But I just want to kind of tell you where we're going and the kind of things that we'll need to be able to do. So in that regard, let's actually look at one of the patches. So imagine I just took one of these yellow patches here and we're looking at it here. And of course, because vectors are important, I want to be able to describe everything in terms of vectors. So I look at this patch and I have this vector running along the patch over here, and I have another vector B running along the patch over here. And of course, talking about how these vectors are situated with respect to each other, angle automatically becomes an important consideration. So for example, now, if I wanted to be able to find the area of this patch, having 2 vectors and being able to find the angle between them can actually be very useful. How can we actually get that to be useful? Well, okay, so here's my patch. What I can do is, instead of thinking of it as this parallelogram, just think of it as like 2 triangles, similar triangles attached to each other, where the magnitude over here is A, the magnitude over here is A and B, and there's the angle between them. And so now I kind of just focus on this, this triangular portion here. And so now I can realize that the area of the patch that I care about, this little area here, is just going to be, well, double the area of this triangle. All right, and so now is where we reach into our high school trigonometry language. How do we find the area of that triangle? Does anyone actually remember? So I have a triangle, and I know an angle, and I know 2 sides of that triangle, and I actually, let's say I know the angle of that's in between these. But this is where you guys chime in. How do you find the area of that triangle? Do you remember any formula that looks like that? Formulas to find the area of a triangle in this situation? No? Okay, well, let me remind you of geometry. Geometry is going to be very important. A formula to find the area of a triangle in this situation is 1/2 times the product of the magnitude of the 2 sides times the sine of the included angle. Okay, so this is A, magnitude of B, sine theta. So 1/2 AB sine theta is the formula that you can use to find the area of a triangle, where theta is at some angle and A and B are sides along that angle. So this expression here is going to be important. And that expression is actually going to be important. You'll actually see that guy pop up as being connected to the cross product. And we'll actually look at that tomorrow. So for now, let's just file that away, that this formula here is going to be important. But ultimately, that leads us here. So the area of this patch will be given by that, and that's important. Now, assuming we can find this area from this formula, of course, I know about the vectors A and B, but how do we know that we can find the angle? How do we find the angle? So now, what about finding the angle? How do we go about finding the angle? So again, here is our vector A and our vector B, and we have a triangle here. How can you actually find the angle in between? And I don't know what I should ask first. Okay, so maybe you guys will know the answer to this because it's not so far back in high school geometry. This is actually something that we covered in the last lecture. Can anyone tell me what this vector would actually be, this black vector? So you know A is going in that direction, and you know B is going in this direction. What is the vector that goes in that direction? Where are my people doing physics should actually know that.
B as a fraction equals A.
Yeah, so how would you describe the vector that, what is the vector here in terms of A and B?
A minus B.
Right. So if you take the vector A and then you subtract B, which means you go in the opposite direction of B, you get the vector that's pointing in this direction. And so that here is the vector A minus B. Right. Now let's call that vector C. So ultimately now we have a triangle where I know, okay, this side is the magnitude of A, that side is the magnitude of C, that side is the magnitude of B, and I know about this angle here. Do you know a way that we can actually find that, and that was the answer to the question here, A minus B. Do you actually know a formula by which I can discover what this angle is?
Could you use the law of cosines?
You can lose the law of cosines. Now, I know you all remember your law of cosines, but just in case I have it right here. Pretend that, you know, this is here, it's the magnitude of A, here it's the magnitude of B, here it's the magnitude of C, and this angle here is our theta. According to this formula, we can actually find that angle, or we can at least find the cosine of that angle. So what we can do then is realize that by the law of cosines, we know that A minus B squared would be the magnitude of A squared plus the magnitude of B squared minus 2 times the magnitude of A magnitude of B cosine of theta. And so I can actually solve for the cosine of theta here, and that can actually get me to the angle theta can be found by just taking the cosine inverse. So I can do something like A magnitude of A squared plus magnitude of B squared minus magnitude of A minus B and over 2 magnitude of A magnitude of B. Okay, so that's how we can find an angle. So we can talk about areas using this formula. We can find angles using this formula, and we'll actually get back to that. Now, there's something else I want to talk about. So this is the area discussion, the angle discussion. Let's actually talk about the directions discussion. Let's talk about that direction consideration that I brought up before. So I have this little patch tilted in space. How can we describe via a direction how that patch is actually tilted? And maybe as a nice exercise, it would be good if someone who doesn't know about cross products and dot products and all that good stuff, maybe give me some ideas, throw some ideas out there. What would you do? Let's say I wanted to describe the direction of this with some vector. Describe direction with a vector. Right. So here's our little patch. What vector do you think would be good to actually describe the direction in which this patch is tilted in space? What kind of vector do you think? Any ideas? No wrong answers. In fact, I kind of want someone who doesn't know what the right answer should be to kind of take a guess. Just be brave and take a guess.
Can you repeat the question? I'm sorry.
Describe with a vector, right? So use a vector, right? Some vector, so it's some arrow that is going to describe how this thing is slanted in space, some sort of the degree of slant or what direction it's moving in. What do you think is a good vector to use to make that description? Just describe to me how you would find it or what vector you want to use.
I'm just confused because you said it's a patch, correct? Like it's exactly.
Yeah, just you can think of it as a small plane if you want. It's a small flat sheet. You know, so it's like, you know how in 2D if we had a line y equals 2x plus 1, and I would say to someone, describe how that's slanted. They would say, well, 2. I can tell you a description of a slope, and this is just a measure of how this is slanted. It's slanted in such a way that if you move 1 unit to the right, you'll move 2 units up. Now, of course, measuring like that in 3 space is not going to work. We are going to measure direction based on vectors. So a vector way to describe how this guy is moving is, say, move 1 here and then 2 there. So a vector description would be the vector, say, 1, 2. but I don't necessarily want you to talk about a specific vector. That would be this vector here that's kind of running along the line. So I just want you to tell me the same idea. What kind of vector would you try to find if your goal was to describe the direction in which this guy is slanted? Go, just take a guess. Go, don't worry about it.
I don't know. I feel like it would be like you'd have to, since it's like it's more than just a single line, like it's a patch, you would have to find multiple vectors. That would be my
Okay.
guess.
Yeah. All right. What are these multiple vectors that you would find?
They would have to be related to the dimensions of the patch.
Okay. So it's two-dimensional, and we're in three space. Like, who would you want to find? If you were to draw on this picture the vector that you would want to find, who would it be?
You mean like on the patch? Like it would
Yeah.
be the patch. I don't know, like the length of it.
So you want like a vector that's running along the length like that?
Yeah.
Okay. And then what?
And also one running along the width.
Okay, so you'd look at two vectors because you know it's two-dimensional. Okay, so you think if we have those two vectors, I can describe the direction. So we want the direction as two vectors.
Yeah, that would be my guess.
So you'd use two vectors to describe the direction of this patch. Okay, that's a very interesting suggestion, and that's actually closer to the answer than the typical first guess would be. So the typical first guess that a student would be, taking intuition from two space, is that they would say, well, we just need some vector that's parallel to the plane, right? So if I know a vector that's in the plane, I can just measure the direction of that vector, and then I can talk about the direction of the plane. You went a little further and kind of realized, yeah, that's kind of not enough. I know something is off here. But yeah, so you're kind of seeing the issue here. But let me actually talk about why a parallel vector is actually not going to be good enough. And for that, probably we need to actually switch back to video. Okay, so let's actually talk about this. So the typical suggestion, which you kind of one-upped on that, which I'm very happy to see you guys thinking, is to, here's the patch, right? This is a book. It's actually a nice book. I like this book a lot, by the way. So here's our patch in space. Suppose we can find a vector that's parallel to this plane or this patch, right? And I want to describe the direction of this patch by the direction of this vector. You immediately have an issue, and the issue would be, well, that vector is also parallel to the plane, and it's pointing in a completely different direction. And then someone can talk about, well, there are multiple vectors that you can take, but that kind of leads you into the same issue. There is no real unique description here. So if a million people want to measure a bunch of vectors in this plane to describe the direction, you could come up with a million different answers. Like someone might, who is going to describe who is the length and who is the width? Like someone might measure this and that, and another person might measure this and that, another might person that, right? It turns out that the parallel vector isn't actually good enough. And so another question you might think, well, if a vector parallel to the plane is not going to work, maybe I need a vector poking out of the plane is going to work. So that would be the next suggestion. And then you'd realize you'd kind of end up in the same situation. So let's say I want vectors that are poking out of this plane at 30 degrees. We end up with the same situation. There are an infinite number of vectors poking out of this plane at 30 degrees that are all in very different directions. So again, a million different people can describe a vector poking out at 30 degrees, and a million different people could come up with a million different answers. And you don't want to be in the situation where you're describing the direction of something that can be interpreted in a million different ways. Now, what about 45 degrees? Now, you'll realize that the same issue is going to happen with every single angle that you're poking out at this vector, except one angle. Anyone want to take a guess?
90, but you want it perpendicular.
Perpendicular. Once you have perpendicular, someone can put the perpendicular base of the vector anywhere on this patch, and guess what? It is actually pointing directly up. And remember, based on what we did with the last lecture, These are all interpreted as the same vector. Now you say, could anyone possibly come up with a different kind of vector? And yeah, they could come up with literally the opposite one, but based on last lecture, that's parallel anyway. They can have vectors of different magnitudes. Once you actually find someone who's perpendicular, that's the guy we want. That's actually going to help us describe the direction of this plane in a unique sense, meaning a million different people could describe the direction of this plane with this vector, and a million different people will come up with the same answer in the sense of at least a parallel answer. So the vector that's 90 degrees to it is the one we would want. Now, such a vector is called a normal vector. That's the proper name for it. A vector that's perpendicular to a plane or perpendicular to anything, we call that a normal vector. And it turns out perpendicular also needs some refinement. When we were in 2 dimensions, there was really only one perpendicular, if you would notice. If I had a line that was non-vertical and it's a non-horizontal, non-vertical, and its slope is m, then I know a perpendicular slope is -1/m, right? The negative reciprocal was the slope. It turns out in 3 dimensions, though, you can be perpendicular in an infinite number of ways. So if this is a vector, this vector is perpendicular, but so is that one. So is that one. So is that one. There's an infinite amount of vectors that are perpendicular to this. So because there's a higher ideal of being perpendicular, we give it a different name. This we call orthogonal. So anything perpendicular, if a vector is perpendicular to something, I said this vector is normal to that thing. It is its normal vector. And to say it's perpendicular in higher than 2 dimensions, we use the phrase orthogonal, just to kind of like a higher dimensional version of perpendicular, just to, in the same way that derivative is a kind of a more refined ideal of slope. No one says slope once you're not talking about a straight line. Everyone says derivative. In the same way, in 3 dimensions or higher, no one says perpendicular. They say orthogonal. Now, I actually mentioned that in the notes, so I'm not going to write that down. Now, here's the other thing. We already discovered that the vector normal to this plane is the one we're going to want. Now the question is, how would we actually measure such a thing? How would I know that a vector is normal to this plane? How would I know it's orthogonal to this plane? So someone might say, well, now we can use the parallel vector. Let's find a vector that's in this plane, and then, boom, find the vector that's orthogonal to that. But now you get into that problem that I mentioned earlier, because you see, this vector that's in the plane is also orthogonal to that. So if I know about just one vector in a plane, that's not enough to determine a perpendicular direction or quote unquote orthogonal direction. So here's where we go with Joe's idea. Let's use two vectors in the plane. Now it turns out that that is going to be enough. If I have 2 vectors that I know they're lying in a plane, and I find something that's orthogonal to both of them at the same time, that's the golden ticket. Because you'll notice, if I try to do like what I did earlier and just move it so that I maintain orthogonality to one of them, I can now lose my orthogonality to the other one. So it's perpendicular to both. Here, I'm now perpendicular to the one, but not the other. Any other direction other than straight up out the plane will violate being perpendicular to both at the same time. So it turns out if we have 2 vectors, we can get this, we can know for sure, okay, if I have 2 parallel vectors that are parallel to the plane, and I find something that is perpendicular to both at the same time, that's the guy we want. That's the normal vector. So it turns out when it comes to direction, slant, slope, thing, an orthogonal vector, a normal vector, is the way that we'd want to describe it. That way, a million different people can come up with a direction. They would all be right. We'll all be on the same page. Everyone will know what we're doing. It is good enough to make a definition. To find such a vector, though, it is very convenient to be able to find such a vector that has that property to 2 vectors at the same time. So in the chasing the idea of being able to find a direction of a slant, we need to be able to find an orthogonal direction. In order to do that, we need 2 other directions to to kind of base that on. And that, by the way, is where the crosswise is going to come in. That's actually in tomorrow's lecture. But I just want to introduce you all the ideas that we're going to need and how we're actually putting them together. So let's now go back to our thing, and I'm going to turn off my video again. Okay, so let's actually fill in the. So the guess is, the right guess here is we need a normal vector. Right? So this is just a vector that's orthogonal to, I wrote it in the notes somewhere here. So we actually need, this is the best direction, some vector that's poking out of this thing at 90 degrees. Now, in order to be able to do that, I need to know about two other things in here where this vector happens to be 90 degrees to both of them, right? And that is a discussion that we'll pick up with tomorrow. That's not the discussion we have for today, but that is just something I wanted you to be aware of. And in fact, I actually have a little picture here. Where am I? 1207. I don't know why I scrolled down all the way there. Okay, let's put in the picture here. Right? So to be able to describe that whole orthogonal direction thing, notice that I need two vectors in that patch. The same patch that we know the area in and all that good stuff. To get something that's perpendicular to it, I need it to be perpendicular to two vectors in that plane. Okay, so these are some important ideas. Let's actually get into solving some of these problems, right? So now we know about some things that we need. We need to know about, well, one, we need to know how to actually find the area of a patch. Two, we need to know about an angle, but how to find angles between two vectors. Three, we need to know about how to find a vector that is perpendicular. From now on, we're going to use the word orthogonal to describe, we need to be able to find a vector that is orthogonal to two other vectors at the same time, right? So to be able to do all the things that we want to be able to do in calculus, we need to be able to do these things, okay? And so now let's actually get around to how would we actually even go about doing these things. Okay, let's start with the area and the angle problem, actually. So let's go back to finding the angle between two vectors. And we actually saw this, but right now I want to actually derive a formula for you, and we're pretending that we're in 2 space. So we're in R2 right now, okay? And what I'm going to show you in R2 is going to generalize very naturally to higher dimensions. So me showing you in R2 is going to be fine. So we saw, to measure the angle and find the angle, I do mean the smallest angle. Right, so if we have two vectors, you can find this angle over here, or you can find that angle over there. We're talking about this one. We want this one. Anyway, we saw to find our angle theta that this equation came in handy. Okay, let's actually get a little bit specific because I know these vectors in their component form. So this would be the magnitude of A1 minus B1, comma A2 minus B2 squared. This would be the magnitude of A1, A2 squared. This will be the magnitude of B1, B2 squared minus, I'm going to leave these guys in their magnitude forms. And let's actually look at what this guy would be. So it's just the sum of the square of the components, and square rooted is the length, but we're going to square that. So this is going to look like A1 minus B1 squared plus A2 minus B2 squared. This is going to be A1 squared plus A2 squared. This is going to be B1 squared plus B2 squared. This is going to be minus All right, let's actually simplify. So this is a1 squared minus 2a1b1 plus b1 squared plus a2 squared minus 2a2b2 plus b2 squared. This is going to be equal to a1 squared plus a2 squared plus b1 squared plus b2 squared minus 2ab. I'm actually writing around the chat box right now. That's why I had this like weird slant. Now let's start to simplify. Subtract a1 squared from both sides. Subtract b1 squared from both sides. Subtract a2 squared from both sides. Subtract b2 squared from both sides. In fact, I'll be able to divide both sides by 2 to get rid of those 2's. And I would be able to actually now solve for the cosine of theta. Now you're going to notice the cosine of theta, what that guy is going to look like is he's going to look like a1 b1 plus a2 b2 divided by the magnitude of that, right? Once I just solve for cosine, and that is the equation that we want, right? This equation is going to help us to find the angle between the two vectors. Now, what I want to point your attention to is this guy right here. Because it turns out that if you do these calculations in any dimension, let's say we're in n dimensions, a1, a2, all the way up to an, something like this will always show up in the calculation. Let me move the chat box out of the way here. Something like this will always show up in n dimensions. It would look like a1 b1 plus a2 b2 plus going all the way up to an bn. You'll see that pattern all the time. Once you expand, you apply the law of cosines, you expand, you collect terms, you group everybody, you solve for cosine theta. The numerator is always going to be that expression. Now, whenever something like that happens, math people like to give that a name. So this expression we call the dot product, right? So that is what a dot product is. Given two vectors like a1, a2 all the way up to an, and another vector b1, b2 all the way up to bn, we define the dot product to be this expression. Multiply the corresponding components, add them together. The sum of the products of corresponding components. We denote that with, yes, there's literally a dot that we put here, and that's very important. It's called a dot product, right? And we write it with a dot specifically. Writing two vectors beside each other without anything in between them is nonsensical for the math that we're doing. So if you have a product of two vectors, you need to identify what kind of product you're taking. And again, as I mentioned last time, product, quote unquote, isn't the same way that we think about product in for real numbers, right? Because technically for division, for vectors, there's no such thing as division. It's hard to actually undo a multiplication, quote unquote. So product, think of this as a loose term. Think of it as this is just an output that is valuable to us when we're given two vectors. Given two vectors, if I want to find the angle between them, this expression becomes immediately important. That expression we call the dot product. Okay, so that's what it is. Now, if I go here and I replace the green with dot product, like A dot B, I get this formula. And so this gives us, you can call it a theorem, you can even call it an alternative definition if you want. This is a definition that's very useful if you know the components. This is a definition that's very useful if you know the vectors and the angle in between them. That is also identifying the dot product. That's just me solving for the dot product version here. So these two equations, very important, you need to know them. And yeah, now you know these two equations will help you on the bonus problem and one part of it. There's something else I'm going to mention that's going to help with the bonus problem later on. But before that, I do want to mention this here. Dot product is a scalar, right? So I take two vectors, I find their dot product, I get this expression here. I want you to appreciate that that is a scalar. Now, why did I say it so aggressively? Well, as a teacher, you realize that you've been teaching for a long enough time, you realize that there are some mistakes that students make that just keep coming up. And whenever you realize that one mistake keeps coming up, and it's just in the broad context of things, relatively speaking, it's a very silly mistake to make, you do want to shout it from the mountaintops after a while. No, this is the truth, right? So that's what I'm doing here. The dot product is a scalar. Every now and then I have students, I'm doing dot products with them, and they're writing down vectors and they put A1, B1, comma, A2, B2, comma, A2. No, the dot product is a scalar. It is a scalar. It is a number that shows up when we're trying to find the angle between two vectors. It will be the numerator of the cosine. So other things, which I'm not going to prove for you, but using the definitions above, you can prove these very easily. These are properties of the dot product. Okay, so, and of course, I'll share the PDF of the notes here, so you don't have to write all this down. Just know that the dot product will obey these properties. And here, I want to talk about now orthogonal in terms of dot product, and this will answer the other bonus problem. So remember, orthogonal, very important idea. We want to know when a vector is orthogonal to stuff. Okay, what does it mean to be orthogonal? Well, it means the angle is 90 degrees. Sipping on my tea here. Which means pi over 2 radians. Now, if we go to this theorem up here, which we know defines the dot product, and I plug in theta equals pi over 2, what's going to happen? Well, of course, cosine of pi over 2 is 0. So what does that mean? If the angle between the vectors, which is, remember, which is what this whole thing is about in the first place, I'm trying to find this angle right here. If the angle between the vectors is pi over 2, what you'll realize is that this theorem tells you the dot product is going to give you the 0 scalar. So that is now a theorem. That is just something we know now. How can I know that two vectors are orthogonal? Well, I can take their dot product, which means product of corresponding components, added them together, I will get a number. If that number happens to be 0, I will know these two vectors that I'm looking at are orthogonal. This is going to be a way that I can verify the orthogonality of certain vectors, right? Give me two vectors, and someone asks me, are these two vectors orthogonal? Are they perpendicular to each other? All I need to do is just do this dot product calculation, just multiply the corresponding components, add them together. Get 0? Yes, they are perpendicular. Don't get 0? No, they are not perpendicular, okay? And that leads us to this little maxim, which we're going to add to this in tomorrow's lecture. There are certain things that you'd want to be able to know. The same way that you know how to describe when two lines are parallel, you know how to describe when two lines are perpendicular, you want to know the same kind of things. So now we know, how can we describe that two vectors are perpendicular? Dot product equals 0. How can we describe that two vectors are parallel? One vector is a scalar multiple of the other, right? So you should know these things just as shorthand. These are just little things. The same way you kind of know, oh, two lines are perpendicular if their slopes are negative reciprocals of each other. Of course, parenthetical statement, neither of them are vertical. Okay, so you just know that. Okay, two lines are parallel if they have the same slope. Two lines are perpendicular if their slopes are negative reciprocals. In the same way, you just should know right off the bat. Two vectors are perpendicular if their dot product is 0. Two vectors are parallel if one is a scalar multiple of the other. And by the way, there's going to be some that we can add to this when we talk about the cross product tomorrow. We're actually going to find another way to talk about parallel vectors. But that's kind of jumping the gun here. But yeah, so that's something that we can know. And yeah, that's the dot product essentially. Now, once you actually know about the dot product, we'll probably finish up some of these examples here. Projection's very cool. I'm not going to cover that with you guys. I'd rather spend the time talking about cross product. By the way, I did set up a lot of things that we need for the cross product tomorrow, so it'll be a lot less rambling tomorrow, and we'll just get right down into the math and getting into calculations. I'll talk a little bit more about how the cross product came to be, where the formula comes from. But for the most part, we kind of set up the conceptual things that we wanted to. Let's actually wrap up now by doing a specific example. So this is going to help. So this will help you with the bonus on the test, right? So there was a bonus that asks you, describe using dot products or cross products. To describe orthogonal with a dot product, it's this equation. So now you guys know. Now, let's actually find a dot product, which is also in the bonus to your problem. So here I have two vectors, A and B. A is 1, 2, 3, component notation. B is 1, 0, -2. Find A dot B. And you literally write the dot. It's important to write the dot. Okay, don't just write A and B beside each other. It actually does not make any sense for us. Okay, what is this going to be? Well, you multiply the corresponding components and you add them together. That's it. So this is going to be 1 + 0 -6. This is -5. Now, the -5, there is some meaning to that. But for us, as far as you're concerned, how you want to think about that -5, it's the guy that's in the numerator of this cosine. Another way that you want to think about this -5 is specifically, it's not 0. So whatever these vectors are, I know for one thing, they are not perpendicular. They are not orthogonal to each other, right? So these two random vectors that I just did, their dot product is a scalar. It's always going to be a scalar. But if it's non-zero, it means they're not orthogonal. How do you actually go about finding the smallest angle between the two vectors? Well, we know that the dot product can be written as the magnitude of A, magnitude of B, cosine theta, which means that my theta can be written as the cosine inverse of, well, A dot B over magnitude of A, magnitude of B, which now we just computed that was -5. And the magnitudes, we just used the formula that we had. So this is going to be square each component added together, take the square root. So that's 1 squared plus 2 squared plus 3 squared, which is, I want to say 14 square root of that. And then you look at B, 1 squared plus 0 squared plus 2 squared. I want to say 5. So it's that. So this is the cosine inverse of -5 over that, or I can, I guess, write as -5 over 14. And that would be your answer. That's the angle between these two vectors. So they're in fact not orthogonal. If I want to know what angle is between them, that. Now, how do you show that this and this are orthogonal? Well, you do the dot product, show that it's 0. Actually, try these examples out. It'll be in the notes when I post them. Try these out for tomorrow, and we'll jump right into them. This one is a little bit, it's a cute example, but if you choose it in a certain way, if you choose the solution in a certain way, it actually will motivate one possible derivation of the cross product, which I'll probably mention tomorrow. But I'm going to actually derive the cross product using the basis vectors, I, J, K. For now, we'll wrap up there. So you now know how to do a couple more problems in the bonus section of your test, where I'm literally going to ask about things like this, where just describe to me how you would talk about these properties in terms of dot products and cross products. But that's what a dot product is. And hopefully you have some motivation as to why we needed these things and where this thing actually came from. Now, I'm never going to actually ask you to actually explain any of this, but I figure it's nice, instead of just starting like the textbook did, where they literally started with this definition. I think it would be nice to kind of tell you where that definition came from and why it's even important. So we'll stop there, we'll wrap up there, and we'll actually complete these two examples tomorrow and go into the cross product. That being said, good luck today. if you work through the mock exams, you should be fine. Hopefully you got the programs to start working for you. But other than that, unless there are any final parting questions, we can go. You can go do some last minute studying. I don't know if you need to, but anything before we go?
Jhevon, can I talk to you after class privately?
Oh, sure. I'll send you a link for office hours if you want to talk to me right after class.
I'm not right now. I mean.
Yeah. Right after I end the class, I'll send you a link.
Yeah, sure. Thank you.
Okay. Anything else about today's lecture? Okay. So your test is at 4:30. Just so you know, I will open it early. So I'll have it open as of 4:15. So in case you want to get in and if you have to restart your browser or anything like that, you have a little bit of cushion. So the timing is going to be, it will be the entire period. So it'll open at 4:15, but the test officially starts at 4:30. Then the test will go until 5:20. Once it hits 5:20, you'll see a timer, but eventually if it hits 5:20, it will kick you out. You then have 10 minutes. You have until 5:30 to upload your answers using the other thing. So by 5:30, you should be done, out and finito, and worrying about bigger things. So that's kind of the timeline. So exam is gonna come live at 4:15. Official start time is 4:30. You need to be done by 5:20. You have a 10-minute period to send in the scans of your work. Okay, all right. And Rolf will be proctoring as always. So if you have any issues with the platform, you can actually reach out to him. I will actually be lecturing during the time that you guys will be doing the test. So don't contact me, like I won't be able to respond. That being said, let's actually wrap up. I think we'll just go. I'll post the video and the notes in a link on the video as always. So that being said, I think that's it. See you guys later. All right, Castle, I'll see you in office hours in a few minutes, and take care.
Thank you. See you.
Take care, everybody. Stay safe.